Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. We're back today with another episode of my look at structural engineer Brian Mullin. As we've seen in the last couple of episodes, he's got some rather strange takes on rather simple physics concepts. We're going to have a look at Newton's law of universal gravity. So cue up the music and let's go.
I realized that there are some very good points being brought up by the Flat Earth community, and that's why I started this series, because I'm really asking for help here. I can't explain these things, and I've got a pretty strong physics background. I took 2 physics courses in high school and then a bunch in college to get my degree, and maybe I'm missing something, maybe I'm not. But one of my favorite sayings in the engineering world is, you learn 10 times more from your mistakes than you do from your success. This is what we always tell rookie engineers. This is what they told me. Don't worry about making mistakes. Don't worry about being wrong. Because when you are wrong or you do make a mistake, you want to find out why. And on the way to finding out why, you learn a ton.
Well, Brian, you're in luck, because fortunately you're about to get a lesson in gravity. Now, we're going to go ahead and have a listen to Brian Mullin and his discussion of the universal law of gravitation in this episode and the Cavendish experiment in the next episode. I've reviewed these rather carefully, and he makes some very severe errors of insight into these experiments and ideas.
And so I've set up a problem here with the Earth, represented by this blue ball, and me or any other man or woman standing on the Earth, and how we determine the weight of that person. Weight is actually caused by the force of gravity of the Earth pulling down on the object, in this case, the person. And so the bread and butter physics equation up here, one of the first equations you learn in Physics 1 is force is equal to mass times acceleration. This is what Newton based all of his 3 laws of motion on. And since his boy Copernicus, 150 years prior, had come up with the solar system, he knew that he needed to come up with an equation that would not only work on Earth, but would work throughout the universe. Okay? And so what this equation says is that the force acting on an object is equal to the mass of that object multiplied by the acceleration that the object is experiencing. Okay? And mass is defined as the amount of matter in an object. And in Physics 1, they hammer into your head that mass is the same throughout the universe. Only weight changes because the gravity on each planet can change. The gravity on the moon is less than it is on Earth. It's supposed to be about 1/6 of what it is on Earth. And so I was taking physics, and I had just taken chemistry, or I was taking it at the same time, I can't remember, but I immediately thought about the fact in the lab we were weighing things in terms of grams. And in the metric system, grams and kilograms are actually units of mass. But to determine mass, we actually weigh it, or weigh an object, and we say this is how massive it is. And so I thought to myself, well, if that's the case, if I took that same scale up to the moon, it would definitely give me a different reading because the force of gravity is less, and that's what's pulling the scale down, right? So how can that be? How can mass be the same throughout the universe? Does that mean we would have to calibrate our scales to work on the moon so that they show the same mass that we get on the Earth? Or do we use a conversion factor instead? Or how does that work? Does that mean that just all mass in the universe is actually defined on Earth?
Well, let's go ahead and unpack this a little bit. First of all, force is indeed mass times acceleration. That's Newton's first law. Weight is mass times the acceleration of gravity. That's what we refer to as weight. Now, if Brian had actually taken chemistry, he would already know the answer to the next question that he had. First of all, he said that he weighed things in the chemistry lab in grams, which are units of mass. And that's very true. They are units of mass. We don't use newtons, for everyday measurements as far as quantities. We can measure a pound of something or a kilo of something. Now, there are 2 basic types of scales. This is a spring scale. Now, a spring scale works by having a plate that you put a mass on, and that compresses a spring. And based on how much it compresses the spring, it will read out a weight. Now, how does it do that, and why does it read out in grams? Well, the very vast majority of all scales that any of us have ever seen or ever will see are used on Earth. There is a fixed value of gravity on Earth of 9.81 meters per second squared. It is very convenient for people to use scales that are calibrated to that gravity to read a particular weight, be it pounds or kilos. You don't weigh yourself on your bathroom scale in newtons. You want to know how many pounds or kilos you weigh. The scale is actually set up to make that conversion for you. It's a very simple conversion. Now, the other thing that Brian hasn't talked about, because it hasn't really come up yet, but it will in this episode. These spring scales not only have to be calibrated, they have to be calibrated if you move them. They're calibrated to a reference mass at a particular latitude. Now, if you move that scale to another latitude on Earth, that same reference mass will give a different reading on the scale. And that has to do with the interaction of gravitational force and centrifugal force. We'll get into that when we talk about Kepler's laws and orbital mechanics. Now, to avoid this problem, Brian could have very easily have gone to his freshman chemistry course and talked about this other type of scale. That's called a balance scale. And the reason that it's called a balance scale is that it has two trays separated by an arm. This arm can rock up and down. So what we do is we put an object that we want to find the mass of on this side, and then we put reference weights on this side until the scale balances. Once we know how much reference weight we need to balance this, we know the mass of our unknown object. This is why precious metals are measured on a balance beam and not on a spring scale. Now, with a balance beam, it will not matter what latitude that you're on. It also would not matter if you were on Mars or the moon, because the force of gravity is affecting both sides equally. They're always measuring a mass against another mass versus a mass against the compression of a spring. Now, Brian starts to go off the rails a little bit and says, well, is mass defined by what it is on Earth? No, it really isn't. Mass is the amount of stuff in an object. We have stuff on Earth, they have stuff on Mars. They're both mass.
So anyway, since weight and mass are different, weight is actually considered to be a force. This force of gravity, we have weight over here and weight here. Weight is equal to the force of gravity pulling me down. Okay? So this equation can be rewritten, F equals ma can be written as weight is equal to mass times little g here. And little g is considered the acceleration due to gravity, or the acceleration at which things fall towards Earth. Now, I posted a link in the description to a trailer for the BBC series, episode 4, Human Universe, in which Professor Brian Cox from the UK, travels to the Glenn Research Center in Cleveland, Ohio, to do an experiment with NASA's vacuum chamber. And in the experiment, they drop a clump of feathers and a bowling ball. And the first time they drop it when there's air in the chamber, the bowling ball obviously falls a lot faster than the clump of feathers. But when they remove all of the air from the vacuum chamber, both the feathers and the bowling ball fall at exactly the same rate. So what this little g says is that all objects accelerate towards Earth at the same rate unless there is some type of fluid preventing them from falling at that rate. And so the more dense something is, the faster it'll fall through the air. The less dense, the slower. It's just like in water. Something heavier or more dense, more massive will sink faster than something that's less massive or less dense.
Now, just in case you were wondering on the bowling ball and the feather example, there were different rates that those objects fell, whether they were in air or they were in a vacuum. It had absolutely nothing to do with density. It had to do with something called air resistance. Now, no matter what mass you have, on Earth, it will fall at 9.81 meters per second squared. All right? The only thing that changes with the mass is the amount of force, but the acceleration stays the same. So, if you drop an object in a vacuum, it will fall down at 9.8 meters per second squared. However, if you have air resistance, that acts as an opposing force. That way. And as we saw with centrifugal force, even though it's falling down at 9.81 meters per second squared, it has a 1 meter per second squared deceleration caused by the air resistance. So the net effect, again, would be something different. That's why it falls a little bit slower. So if you have a very light object with a large surface area versus a very massive object that has a small surface area, the massive object will fall faster because there's less air resistance. A feather has got a lot of surface area and very little mass. A bowling ball doesn't have much surface area and it has a lot of mass. However, if you took two bowling balls, an 8-pounder and a 16-pounder, and you drop them from the same height in the same air, they'll both hit the ground at the same time. Because their surface area is approximately the same, the force of gravity on them is the same. If density was the driving force behind this, that bowling ball would fall twice as fast as that bowling ball because they have the same volume, but one has twice the mass as the other, therefore has twice the density. That does not occur. Objects do not fall due to density. Density is not a force. Gravity is.
So if I say my weight is 160 pounds force, the metric system would be 72.6 kilograms times 9.81 meters per second squared equals roughly 712 newtons. Okay? That's my weight in metric units. So, over here, we have the equation due to gravity. Okay. And that says that the force of gravity is equal to the gravitational constant times the mass of one object, in this case me, this is represented by a little m, times the mass of another object, which would be the Earth, divided by the distance between them squared, which in this case would be the radius of the Earth. So if you plug the mass of Earth, which I have written here, which is 5.9726 times 10 to the 24th kilograms, really big number, my mass, 72.6 kilograms, and the gravitational constant, and the radius of Earth, which is 6,371,000 meters, you will get 712 newtons, roughly. Pretty close. Close enough to say it's the same. To say that to accept the fact that, well, the assumed fact that gravity is causing this weight. And that's why I have weight is equal to the force of gravity on here. Okay? This is what is taught in physics. That this force of gravity actually creates my weight, but there's just two different ways we can calculate it. Okay?
Alrighty, so let's take a moment and talk about this rather remarkable equation. As originally put out by Newton, that's what he said, was force was proportional to mass 1, mass 2 over the radius squared. Now, what does proportional mean? It means that when you change these values, you change that. Now, the difference between these two equations is that this will give you a very specific number of newtons. That'll just tell you what happens when you change the masses or the radius. Now, there's something that I should really clear up when people view my videos. When I talk about the force of gravity, I live in a Newtonian world. All right, I'm very, very aware of the fact that Einstein has got a better description of this thing that we called gravity than Newton did. However, for the normal situations in the world, if we're not dealing with black holes, if we're not dealing with objects approaching the speed of light, if we're not dealing with tiny little objects, you can use Newtonian physics without fear of error. And since Newtonian physics are much simpler to do than the advanced calculus of Einstein, most people work with Newtonian physics, be they engineers, be they artillerymen, be they science guys on YouTube. We are going to work with Newton. If you have a problem with that, fine. You have to do the math to show me that Einstein will give you a different answer than I got using Newton. And that difference needs to be significant enough it will change the outcome of either the equation that I'm using or the example or whatever. So don't put any crap in the comments about, Einstein superseding Newton. Newton still works. Newton's still used every day. I'm going to be using Newton unless you can show me I have to do something else because you did the math.
But Newton came up with this before he came up with the equation for gravity. And in fact, Newton only proposed the equation. He didn't actually finish it. He said, from looking at the solar system model and watching things in the sky that he thought, or he assumed were orbiting Earth based on Copernicus's work, that the force of gravity was proportional to the mass of one object times the mass of another object divided by the distance between them squared. Okay? He said they're proportional, they're not equal. So what this means is, if either one of these masses go up, or both of them go up, the force of gravity also goes up. But as the distance between them increases, the force of gravity goes down. And as you can see, this is square, so distance plays a big part here. So he eventually proposed that he needed this big G up here, this gravitational constant. And he didn't know how to determine that, but he did know that the units would be what we have right here, meters cubed over kilograms times second. Now, he might not have been using the metric system then. I haven't actually looked into that, but he would have been using something similar. So I'm just going to assume that he used metric units, because if you combine the units in this proportion right here, you would get, assuming the masses are measured in kilograms, you would get kilograms squared over meters squared. And if you multiply that times this factor down here, you will end up with kilograms times meters a second squared, which is equal to a Newton, or a unit of force. Okay, just like I showed in the original equation, the original bread and butter equation over here. So that said, he theorized that there was this gravitational constant, but he didn't actually figure it out before he died. And it wasn't until a little over 100 years later, about 120, 130 years later, that a man named Henry Cavendish came along.
Well, I've got to tell you, there's not really much that Brian said in this episode that set my hair on fire. He made a couple of small errors, and he had this annoying habit of constantly throwing in qualifiers that were unnecessary. Gravity is 9.81 meters per second squared, or so we're told. The Earth is spinning, so we're led to believe. The mass of the Earth is, well, according to NASA, these things were all figured out long before NASA came around, so just quit with the editorializing, Brian. Now, in our next episode, it's going to be different because Brian tries to take on the Cavendish experiment. That absolutely went off the rails almost immediately from the start, and it never stopped. It just never slowed down. It just went to the edge at light speed. So until then, this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. Make sure you hit that little like and subscribe down there. I really could use your support of this channel. It's a new channel, and I'd like to build it up a little bit. Take care, guys.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep. soar above the science guy, above the science guy.